Good day, Doctor. We are from Group 17. My name is Ketana Perempuan K. Palamani and my matrix number is A1743889. So the article we choose to present today is comparison of SARS-CoV-2 sequencing using ONT GridION and Illumina MiSeq. With COVID-19 cases has been increasing, WHO declared SARS-CoV-2 as an ongoing pandemic which requires continuous surveillance to understand and identify the virus as well as to develop diagnostic tests, vaccines, and to get genetic information about the patient's infection. Sequencing the SARS-CoV-2 genome is very important. To do so, multiple next generation sequencing technology is being used. So on this article, it mainly focuses on Illumina MiSeq and Oxford Nanopore technology. The major challenge with whole genome sequencing is obtaining whole viral genomes from clinical samples promptly. Both the technology has its own limitations and advantages. As I have listed it down in the table, Illumina sequencing usually requires high cost and is limited by long sequencing time with relatively short reads. On the other hand, nanopore technology is not expensive and can sequence in real time. Furthermore, highly accurate consensus sequence can be achieved, but low quality genome will be produced, which is a minus in nanopore technology. Not just that, it has a low raw read accuracy and with high number of false negatives. And importantly, it failed to detect short index, which can be identified by Illumina sequencing. Well, this is a plus in Illumina sequencing as it provides high accuracy data when done in large batches. The objective of this study is to determine whether the nanopore sequencing is a viable alternative to Illumina sequencing for rapidly identifying SARS-CoV-2 variants found within the African countries. Also, it has been hypothesized that nanopore sequencing will produce more consensus genomes than Illumina.
Hello, my name is Nur Amira Atira and my matrix number is A174735. I will talk about methods. There are two main methods in this journal. First, Illumina MiSeq library preparation and sequencing. In this method, index pairs and libraries were prepared according to the manufacturer's instruction using the Nextera DNA Flight library prep kits Illumina. Amplicons generated from tiling PCR were segmented to allow for the cleavage and tagging of unfragmented DNA. Genome Detective and the coronavirus typing tool were used to assemble FASTQ files generated by Illumina MiSeq. After that, Diamond, a protein-based alignment method, is used to identify potential viral reads. Locality reads are filtered and the adapters are trimmed with thermometric. Short reads are sorted and organized into groups, and de novo metagenomic assembly is performed on each group using spades for single-ended reads or metaspades for paired and reads. The taxonomy ID of the lowest common ancestor of the hits identified by Diamond is then used to identify each group. BLAST-X and BLAST-N are used to search for candidate references sequences against the NCBI-RefSeq virus database. The Advanced Genome Aligner combines the results for all detected candidates, and Genome Detective calculates a score at amino acid and nucleotide level. The second method is ONT GridION library preparation and sequencing. The amplicons generated by tiling PCR were prepared for nanopore sequencing using the ONT native barcoding expansion kit according to the manufacturer's instructions. Chromin 106 flow cells were used to multiplex libraries, which were then run on the GridION X5. No template control from the PCR amplification step was added. The Mino software app was used to monitor sequencing performance in real time. After sequencing, the reads were aligned to the Wuhan Hu1 reference genome. Arctic tool align trim was used to trim primer sequences from the termini of read alignment. Sequencing depth was limited to 400 full coverage. Nanopolish was used to identify variant candidates.
Hi, my name is Nur Amina Shazwani Mitinazali with the number matrix of A174409. Today I will be presenting about the result and discussion for this article. This is the table of comparison of sequencing run 116 on both the MiSeq and the GridION. Thus, in this table, we will be focusing on the runtime and the average coverage. The sequencing runtime for run 116 on the MiSeq was 36 hours, while on the GridION it was 21 hours. Thus, the sequencing runtime for run 116 on the GridION is much faster than the MiSeq. Moving on to the average coverage, consensus genome coverage was significantly greater with the MiSeq when compared to the GridION. This will result in a significantly lower genome quality obtained from the GridION than the MiSeq. These low-quality genomes cannot be used to confidently acquire information on the affecting virus strain and are generally removed through a series of quality control checks. Previously, we talked about the sequencing runtime for run 116 on the MiSeq and also on the GridION. Thus, the article concluded that the GridION is faster than the MiSeq, but it turns out although more consensus genomes can be produced using the GridION than the MiSeq, the GridION will produce more low-quality genomes, which will eliminate the advantage of having a large number of consensus genomes produced. It should be noted that the quality and coverage of consensus genomes for the GridION can be increased by pooling lower samples, as the number of reads and data produced will be shared across a smaller group. So that is all from me. I will be passing on to the next presenter. Thank you.
Hi and Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Farasha Izzati binti Alias with matrix number A174442. So as it can be seen here, the higher genomic coverage for the Illumina MiSeq has been associated with lower CT scores. So CT score is a value that refers to the number of cycles required to amplify viral RNA to a detectable level. So there is therefore an inverse relationship between CT score and also viral load. Okay, so in this investigation, we also noted an inverse relationship between CT score and also genome coverage for both GridION and MiSeq sequencing. So as for the mutation, it has been shown that long-read sequencing platforms have a high error rate, which is mostly indels that are assumed to be randomly distributed within each read. So prediction and interpretation of protein sequences may therefore be critically affected due to the frame shift and also premature stop codons that may be introduced by the indels. Thus, there was a significantly greater number of mutations detected by the MiSeq than the GridION. Thank you.
Hello, my name is Siti Nur Anissa binti Lehan, A174741. We'll continue the presentation by explaining the conclusion and giving comments on the journal. The results of this study shows that the MiSequence is more favorable for SARS-CoV-2 genomic surveillance, as successful genomic surveillance is depending on high-quality near-whole consensus genomes. Even though ONT GridION is less ideal than the Illumina MiSequence for SARS-CoV-2 genomic surveillance, it can be used to produce consensus genomes from samples of high quality and low CT scores. Healthcare facilities, on the other hand, can use ONT sequencing platform to diagnose patients quickly, as the GridION can sequence up to 480 samples every 21 hours. This could help stem the spread of the disease by allowing for the identification and isolation of infected individuals. As for the comments, I found that the objective is not stated in the abstract but lies somewhere in the introduction. The method used in this study is clearly explained in the journal. All points raised in the methods are answered in the results. Also, the summary of the results is clearly stated in the conclusion. However, the hypothesis which is stated in the introduction is not valid. In my opinion, overall this journal is good. That's all from us. Thank you.